Okay, so the quiz is going to be multiply 5 times 10 to the 40th by 3 times 10 to the negative 14th. Then 7 times 10 to the negative 5th over 2 times 10 to the 7th. That's a division. And then we want to simplify the quantity x plus 3 times the quantity x minus 5. And what I mean by simplify, I should probably write that, expand. And simplify. In other words, do the multiplication and then simplify your result. With the scientific notation, got 5 times 10 to the 40th multiplied by 3 times 10 to the negative 14th. You want to do this in about at least 3, maybe 4 steps. Okay, so we got I'm going to put parentheses around the numbers, the scientific notation numbers. We got 5 times 10 to the 40th in parentheses, multiplied by 3 times 10 to the negative 14th in parentheses. Okay. That's the same as 5 times 3, because you got a bunch of multiplications here. You could actually remove all these parentheses because everything is a multiplication. Every operation is a multiplication. And then that's times 10 to the 40th times 10 to the negative 14th. Now I'm going to put parentheses around the 5 times 3 and around the 10 to the 40th times 10 to the negative 14th. So I've just rearranged the order of these multiplications. 5 times 3 is 15. 10 to the 40th times 10 to the negative 14th is 10 to the 40 minus 14. Don't skip that step and do it in your head. It takes about 3 seconds to write it out. And if you write it out, you reinforce, as I say again and again, you reinforce the rules and you reinforce what you're doing. As I've said before, if you want me to give you 100 problems for every assignment, so you practice and learn the rules by rote rather than thinking about it, I can do that. Okay? And I'm not threatening to do that. Like I could give you that as an alternative if you're having trouble. But if you write out every step this way, I think the 10 or 15 problems that I ask you to do for every assignment will be enough. Okay. 15 times 10 to the 40 minus 14. Well, all we got to do is subtract 14 from 40. That's 10 to the 26th. Now, this is not yet in scientific notation, because in scientific notation, you have to have the number out front between 1 and 10. It can't be 10. It could be 1. Okay? Well, 15 is the same as 1.5 times 10. We understand that. 1.5 times 10 is 15. When you multiply by 10, you get to move the decimal over 1 place. And of course, that's 10 to the 1, and we probably want to write out that exponent, because now we see we have 1.5 10 to the 1 times 10 to the 26th by rules of exponents is 10 to the 1 plus 26. I wish that 10 had come out a little bigger. Okay. Which is 1.5 times 10 to the 27th. Now I said 3 or 4 steps, I've actually got 7. There are actually 7 things you have to know, 7 things you have to do to simplify this, and you don't want to shortcut that. reason I do 15 problem assignments is I don't think anybody's going to do 100 problems. But we're trying to condense a year of high school algebra, actually 2 years of high school algebra into one semester here. And to do that, you really need to deeply understand the rules and write them out every time you do an operation for homework. And then get in the habit so you write them out here. You'll learn it much better. And I've only seen 2 tests, one from a distance course and one from this course, and they both passed. Okay? They both had, well, a few flaws here and there and things you want to do. So, you know, everybody that has so far taken a test is doing okay. But I'm concerned about the majority who haven't yet taken it. The deadline's tomorrow. There's plenty of time. Okay. Well, let's look at this one. I'll save this expansion for just a little later when I have plenty of board space. We've got 7 times 10 to the negative 5th divided by 2 times 10 to the 7th. Well, I could write that as 7 over 2 multiplied by 10 to the negative 5th over 10 to the 7th, can I? That's perfectly legitimate because I still have 7 times 10 to the negative 5th for the numerator. And multiply the numerators, this is what I get. And if I multiply my denominators, I still get 2 times 10 to the 7th. So this product of fractions is equal to this fraction. That's a very important point that people don't seem to pick up well. Now, I'm not just talking about here, I'm talking about even in a pre-calculus class. Okay? So we're trying to get that out of the way here. So when you get to a pre-calculus class or any other class that you have to do algebra in, you'll understand that principle. I multiply the numerators of these, I get these. So I know if I have these, I can write it as this times this. I could also write it as 7 over 10 to the 7th times 10 to the negative 5th over 2. I would still have the same numbers in my numerator and in my denominator. But there's no point in doing what I just said. This is the thing that there's a point in doing here. So 7 halves is 3.5. And what's the rule for dividing two numbers, the same number to different exponents? This is the same as 10 to the negative 5 minus 7. Is when you divide, you subtract the exponent. And that gives us 3.5 times 10 to the negative 12th. Now we've actually got fewer steps in this problem. There are only 4 steps. I didn't have to, you know, the number in front of my multiplication came out between 1 and 10. So that was okay. So we didn't have a couple of steps we didn't have to do here. But similar to this problem, I just had to rearrange the numbers out in front and the powers of 10 so that I could operate on them. Over here, I arranged them so I had them multiplied because that's the way it is in this problem. And down here, I rearranged it so they were divided. Okay? All right. Well, actually, I do think I have enough room to expand this expression. And it'd be helpful if I wrote the parentheses in the right direction. Let's try again. Okay. Now, by the distributive law, x plus 3 times something means you multiply x times that something plus 3 times that same something. And of course, that something is your x minus 5. So we have x times the quantity x minus 5 plus 3 times the quantity x minus 5. And that then is equal to, we just apply the distributive law again. X multiplied by the quantity x minus 5 means x times x minus x times 5. So that my x times the quantity x minus 5 becomes x times x minus x times 5. And then we have 3 times the quantity x minus 5. Well, that's 3 times x minus 3 times 5. I don't write x times x as x squared because I want to see every factor and every term represented in this step, just to be sure that you understand why each step is what it is. So that's not something I recommend that you skip. It takes a little longer, but it sinks in a whole lot better and a whole lot more quickly. Well, then x times x is x squared. And minus x times 5, well, I'm going to take the whole step, right? That is minus 5x. And 3 times x is 3x minus 15. And now we simplify. So we've expanded it. Here it is expanded. We get x squared minus 5x plus 3x minus 15. Now we simplify. Negative 5x plus 3x is negative 2x. There's actually distributive law involved with that too, but I'm just going to say, if you got negative 5 times something and add 3 times that same thing, you're going to get negative 2 of that thing. So ultimately, the quantity x plus 3 times x minus 5 is x times x minus 5 plus 3 times x minus 5. X times x minus 5 is x times x minus x times 5. 3 times the quantity x minus 5 is 3 times x minus 3 times 5. X times x is x squared. X times 5 is the same as 5x, and negative x times 5 becomes negative 5x. 3 times x is just 3x, and negative 3 times 5 is negative 15. And then negative 5x plus 3x is really negative 5 plus 3 times x, which is negative 2x. And my final result is x squared minus 2x minus 15. I recommend when you're expanding things, you do every step. Now, a lot of times you'll be taught to do in open math will do this. X multiplies x, x multiplies negative 5, 3 multiplies x, 3 multiplies negative 5. That's good because everything multiplies everything. And that's useful, but you have to understand that's exactly what the chain rule tells you, or what the distributive law tells you to do. You've got your x times x minus 5 because you got x times x, and you got x times negative 5. So right there is your first step. And then you've got 3 times x and 3 times negative 5, which is 3 times x minus 5. So you get immediately from the first step to the third step I drew here. Okay. So you could send that, say that, okay, that gives you the x times x minus x times 5 plus 3 times x plus 3 times -5. And then I'll just write etc. I'm not sure that etc is even going to come out on the screen. I'm still having trouble getting the camera to behave well. You still don't get the etc. There it is. Sort of. There's the top of the etc. And now the board's all tilted. All right. Does that all make sense? Try to do the way I do. I would go back to the assignment and write at least a few of them out in full detail. Just to review, make sure you understand it for later. Like when you get a test, okay? Or when you encounter it someplace else. All right. Well, I want to go on with the distributive law because what we're talking about today is polynomials. So I'm going to give you a bigger one. So you've got plenty of board over here. We want to do this one. Now I'm going to give you just a hint. The first thing you want to do is multiply the first two factors, the first two binomials. And then you're going to multiply that by the third one. And you want to write out every step. So I'm going to put these examples up here where you can see them. Try to follow procedures just like the one I did. Okay, now everybody did the natural thing, which is to concentrate multiplying x plus 3 by x minus 7. Well, that's exactly what we did over here. I gave you, oh, sorry, x plus 3 times x minus 5. I don't know, my catch is a 7, then everything's a 7. But anyhow, that means you're going to have to put whatever you do here into parentheses and then write the x plus 7. What goes in these parentheses is x plus 3 times x minus 5. Okay, well, that's, of course, just as before, x times x minus 5 plus 3 times x minus 5. Now you go to the next step and you put parentheses around whatever you're going to get here. Grotesque looking 7. And do the next step in these parentheses. Okay, and finally, you fill in the steps, which I'll fill in while you're working because you know what the steps are, everybody's got them. You're going to have x squared minus 2x minus 15 multiplied by x plus 7. Okay, and then you've got steps in here. I'll write them out, but go ahead and see what you're going to do with this now. See if you can figure out what you do with this. Oops. Got ahead of myself. Okay, now these steps are exactly the same as the ones I did here, but every one of these has an x plus 7 tacked onto it because he had an x plus 7 here. You can't just leave that off. Just because you're trying to do this doesn't mean you get to leave off the x plus 7, okay? Okay, now some of you have got the pattern and very well, but some people have a little trouble getting started here, and I kind of expected that, okay? Usually in a class, about half of them will see the pattern and half of them will need a little hint. So I'm going to give you a little hint. The first thing you're going to do here, this x squared is multiplied by x plus 7. That's the first thing you're going to write out, okay? After you write that out, then what? So I'm just going to put a few dots here to indicate you got to continue this. Okay. So everybody picked up on that hint and everybody did the right thing. Some of you didn't need the hint because you were already on track with it. Some people did, and that's fine because all I care about is you picked up on it. Okay. Well, if we continue the usual pattern, now some of you that did it right did it just a little differently than I'm going to do it. You chose to multiply the x by this and then the 7 by this. It's perfectly valid. There are two ways the distributive law is stated. One is from the right-hand side, one's from the left-hand side. Okay? So they're equally valid. But I'm going to do it from the left-hand side just to be consistent with the way I've always done it before. Okay, because it's going to be less confusing to people who don't see it from this side. Okay, so you got x squared times x plus 7 is the x squared multiplies the x plus 7. Well, so does everything else in here multiply the x plus 7. That's what this expression means. So you got minus 2x times x plus 7 minus 15 times x plus 7. Okay, well, that shouldn't be a big surprise because, as I say, as soon as I gave you this hint, everybody got it. Not saying everybody got every step, every term of this right, but everybody got most of the terms right. And any term that got wrong was just a little confusion about exponents or multiplication or something like that. The pattern, I think, is clear to everybody. Okay, well, now the rest is pretty obvious. We got x squared times x. Oh, come on. Plus x squared times 7 minus 2x times x minus 2x times 7 minus 15 times x minus 15 times 7. And then that comes out, x squared times x is x cubed. And 7x squared times 7 we'll write as 7x squared. And 2x times x is 2x squared, and there's a minus on that, so it's 2x squared. And minus 2 times 7 is minus 14. Minus 15x is just, that should be 2x times 7 here. Okay, I made a little mistake. When I multiplied the minus 2x times x, I got minus 2x times x, but then when I multiplied the minus 2x by 7, I left the x off. And that's what I mean by little mistakes. A couple of people made little mistakes like that. Now, if I make it, it's a big mistake. If you make it at this point, it's just a little one, but we got to fix it. Okay, so let's fix it. Okay, so that should be 2x times 7. So the step before the one I'm working on, where we took x squared times the quantity x plus 7 minus 2x times the quantity x plus 7 minus 15 times the quantity x plus 7. On the middle quantity, negative 2x times x plus 7, I wrote negative 2x times x. And then I wrote negative 2 times 7. Well, no, it's negative 2x times 7. So we've fixed that. So now in simplifying, when we get up to where I had negative 2 times 7, it should be negative 2x times 7, which gives us negative 14x minus 15x minus 107. Okay, I think everybody got that. That was a good thing to put this. Apparatus here, but it's blocking my arm. Okay. X cubed then, we have 7x squared and minus 2x squared, which gives us, well, 7 minus 2 is 5. So it's got to be 5x squared. And then we have negative 14x minus 15x. Well, that's negative 29x. And I wrote, I've just got this thing about sevens. I've got 15 times 7, which I know is 105, but what did I write? I wrote 107. I have to leave sevens off everything. So don't do that. I'm sorry. So again, instead of negative 107, it's negative 105 in the previous step. So when we do the negative 14x minus 15x, we get negative 29x. And then we've got minus 105. And there it is. Now I can kind of check it. If I go back to the original, I've got an x times a negative 5 and a 7, which is okay, well, that's negative 105x. And this x is times a 3 and a 7, that's 21x. And this x is times a negative 5 and a 3, which is negative 15x. So when I look at this, not everything appears to check out. On the x's, but I think they do. I actually don't see. Yeah, I don't see an error. That doesn't mean there isn't one. Is that what you got? Oops. Somebody just stepped out. Hey, let's just see what everybody got. Make sure I'm not misleading you. Now we want to move along. And I think we're doing pretty well with the distributive law. And we want to move along to, let's just take this polynomial. What the heck, I'm going to add it to my x squared minus 2x minus 15. Okay. So I'm going to get polynomial x cubed plus 5x squared minus 29x minus 105 plus x squared minus 2x plus or minus 15. Okay, so I have in parentheses x cubed plus 5x squared minus 29x minus 105. And then I'm adding the quantity in parentheses, x squared minus 2x minus 15. And just to make it a little more interesting, I'm going to do subtraction here. So it'll be a better illustration. Okay, so take a minute and see what you can do with that. Okay, people were having trouble getting started, and I forgot to record while I was writing this. But I just said that, okay, you have this first term in parentheses, okay? This first sum of terms in parentheses. Then you have minus parentheses x squared minus 2x minus 15 in parentheses. Okay, that means you have minus the x squared, you have minus the negative 2x, and you have minus the negative 15. So, see what you get in the next step. In other words, we're simplifying. Okay, now there's a little fundamental glitch in pretty much everybody's understanding here. Okay, minus x squared is just minus x squared. But you got two minuses in front of the 2x, right? You got minus 2x. But what do you do? What do you get if you multiply two negatives? You get a positive, right? Well, that's like minus 1 times minus 2x if you like. But minus 2x is plus 2x. It's just the way the signs work. And it might look a little bit weird to you. I'm pretty sure everybody knows how to multiply signed numbers. But that's the way it's going to come out. Minus 15 is going to be a plus 15. So in the next step, we've got our x cubed plus 5x squared minus 29x minus 105. And we've removed the parentheses because there's nothing in front of it. And there are only additions and subtractions on the other side of it. So we have minus x squared then plus 2x plus 15. Now, how do we simplify that? Okay, now there's another confusion. So I'm going to do an extra step to make sure we understand that, okay? I can write this with my x squareds together. First of all, I've got x cubed. I don't have any other x cubes. So I've got x cubed. That's going to be part of my final answer. Then I've got plus 5x squared minus x squared. So I've got x squared terms here and here. Okay. Then I've got x terms, negative 29x and 2x. Little circles around those, minus 29x plus 2x. And then minus 105 plus 15. Now I can add negative 105 and 15, and I get negative 90. So that's taken care of. My x cubed is okay. What's 5x squared minus x squared? This is same as 5 minus 1 times x squared. How do I know that? Well, if I use distributive law, I get 5 times x squared and minus 1 times x squared, which gives me 5x squared minus 1x squared, but I don't bother to write the 1. Okay. And then this is, I'm going to say plus Negative 29x plus 2x. Well, actually, I want to write that. What I wrote is incorrect. It's negative 29 plus 2 times x. And again, that's got to be right because I can check myself. Negative 29 times x, well, there it is. And plus 2 times x, there it is. So now I have x cubed plus 4x squared minus 27 times x minus 90. And in the unlikely event that I did everything correctly, that should be correct. Now, do we understand that we got a 5x squared and a negative x squared? That does give us 4x squared. Why? Because I can write the 5x squared minus x squared right next to each other. And then I can write that as 5 minus 1 times x squared using the distributive law backwards. We say we're factoring out the x squared. And same thing with the negative 29x plus 2x. I can write that as negative 29 plus 2 times x. Now, the way I've said that before is, if I've got 5 of these things, x squared, and I take one of them away, minus x squared, right? I end up with 4 of them, okay? And if I got negative 29 of these and 2 of these, I've got negative 27 of them. But formally, the distributive law tells you why that works, because some people are a little confused. They're trying to do x cubed minus x squared. And there's no rule for doing one power minus or plus another power, except that you can kind of factor like this, but we're not doing that right now. Okay, so let's try another one. I'll see how much board I've got visible. Okay, I need just a little more. Let's try x to the 4th. Let's try 3x to the 4th plus 5x squared minus 7. Oh, there's a 7 again. Yeah, we'll do it anyway. Minus 7 plus. And I'm going to throw just a little, I'm going to have another minus here, actually. I threw a little curve at you, but probably less a curve than I had before. Let's see. I'm going to say minus 4 times x cubed plus 3x squared minus 2. Write that down and see what you can do with it. Only got a couple of minutes, but see if you get started on it. Okay, without going into too much detail, because we're pretty much out of time, I've got 3x to the 4th plus 5x squared minus 7. And then it's minus 4 times everything in here, which means it's minus 4 times x cubed minus 4 times 3x squared minus 4 times negative 2. Got to multiply that 4 by everything. There's a strong tendency to multiply it by the first thing and forget to multiply it by the rest. But you have to understand what the distributive law tells you. Well, that gives you 3x to the 4th plus 5x squared minus 7 minus 12, or minus 4. Try to multiply the 4 by the 3. Do what my eye does. Minus 12x squared plus 8. Minus 4 times negative 2 is 8. Minus 4 times 3x squared is minus 12x squared. Minus 4 times x cubed is minus 4x cubed. So we have 3x to the 4th plus 5x squared minus 7, just what we originally had. And then minus 4x cubed minus 12x squared plus 8. Now we group the powers. We have 3x to the fourth, and that's the only x to the fourth we have. And then I try to do it in order of powers. We have a minus 4x cubed, so I'm going to write that down next. And then we have a 5x squared and a negative 12x squared. And then we have a minus 7 and an 8. So we have 3x to the fourth minus 4x cubed plus 5x squared minus 12x squared minus 7 plus 8. Well, minus 7 plus 8 is plus 1. We only have one x to the fourth term, so we don't have to write down anything else there. And only one x cubed term. And then we've got 5x squared minus 12x squared, which I'm going to write down, and I want you to do that. I write that as 5x squared minus 12x squared is 5 minus 12 times x squared. All right. Now, we got our 3x to the fourth that we'll write again. We've got our minus 4x cubed that we'll write again. Plus 5 minus 12x squared, that's plus negative 7x squared. And then we still have our plus 1. One more step, plus a negative 7x squared is just minus 7x squared, isn't it? And then out in front of that, we got our 3x to the fourth minus 4x cubed. Okay. So we're a couple minutes over. I apologize for that. But should still have time to run. And we still got 6 minutes to next class. Okay, knowing that you're focused on the test, there are a couple of things we're going to do today that I think you can really kind of lock in without having to do too much review. Okay. I mean, anybody taken the test yet? You fool. No.
It's the only time I had.
Yeah, I know. Well, it's due tomorrow. So you're as prepared today as you probably would be tomorrow. But you went to the last minute. Okay, anyhow. Total momentum. These are actually vectors. But since everything's implicitly moving along the same line, we can just use plus and minus signs. Instead of, we don't need i's and j's. The I will could be understood if this is along the x-axis. So that would be we're skipping a step here because everybody got this, I think. Mass times velocity, 5 kilograms times 10 meters per second. It's supposed to be a second, but I wrote meters squared. 10 kilograms times negative 7 meters per second. So we get 50 kilogram meters per second minus 70 kilogram meters per second, which is 20 kilogram meters per second. Now, what's the total momentum after collision? Exactly the same as it is before collision. Why is that? Because the impulse momentum there. Now, implicitly, this is an isolated system. There's no other force acting on these things. Okay? No gremlins, no friction, no whatever. Okay? So the total momentum after will equal total momentum before. What's the relative velocity? Well, just ask yourself, if you're sitting on this thing, then how fast does this thing appear to be coming toward you? Let's just talk about that for a second. Okay, now nobody got the relative velocity. We talked about this in class last time. But of course, with the test imminent, nobody paid any attention to what we did in class last time. That's human nature. Okay? Which is why we're doing this now. So that took a while to get the right relative velocity. Okay, we had to go back to two cars driving down the interstate. If I'm moving along at 60 miles an hour and you're beside me moving along at 60 miles an hour, some people wanted to add 10 meters per second and -7 meters per second to get 3 meters per second. Doesn't make sense. Think 60 miles an hour here, 60 miles an hour there. What's our relative velocity? Well, if we're moving at 60 miles an hour later, I look over and you're still sitting there smiling at me. Or whatever you're doing, making gestures. That wasn't amusing enough to cough over. So our relative velocity is 0. We're not moving relative to each other. We're moving right along relative to the road, but we're not moving relative to each other. Now, if you're doing 61 miles an hour and I'm doing 60 miles an hour later, you're a mile ahead of me. You've moved at a relative velocity of a mile per hour. Now, if it's 60 miles an hour this way and 60 miles an hour this way, and we're on a collision course, hopefully we're on a 2-lane road and we're going to both stay in our lane because we're both going to die otherwise. Okay. What's our relative velocity? It's 120 miles an hour. Okay. We're closing at a rate of 120 miles an hour. In here, these things are closing at a rate of 17 meters per second. Okay. Now, from the perspective of the first, mass, perspective of V1, the relative velocity is -17 meters per second. That should be obvious because if I'm V1 and I'm regarding this as a positive direction, then you're closing with me in the negative direction. Okay. So for those reasons, the relative velocity from the frame of V1 is -17 meters per second. I really shouldn't even say from, I should just say in. The frame of V1 of mass 1. Let's be clear what I mean by mass 1. This is mass 1, this is mass 2. In the frame of reference of this mass, the relative velocity is -17 meters per second. Okay. So we have the total momentum and the relative velocity before collision. Also, you don't want to necessarily memorize this as a formula. It's just common sense. If I am in the frame of V1, then I perceive the relative velocity here to be V2 minus V1, because that's the one that gives me the answer that's common sense. It's -17 meters per second. That's a common sense answer. You shouldn't need a formula to calculate that. Okay. Now, sometimes you got weird symbols and stuff like that, and you got to use a formula. The formula is this because common sense tells you what it is. Because that's what we mean by relative velocity. You don't start with the formula and just use the formula to get it every time without understanding what it means. You need both. But in my world, I think the common sense comes before the formula, and the formula is trivially true because of common sense. Still, use the formula, use common sense, and make sure you got them reconciled. Otherwise, you're gonna make mistakes like, well, relative velocity, if you add them together, you get 3 meters per second. Seems obvious you should add things. No, you don't add, you subtract. Relative velocity, you're always gonna subtract the velocities one way or the other. If you want the relative velocity of this mass with mass 1 with respect to mass 2, then it's going to be V1 minus V2. It'll be the opposite. Why? Does that make sense? Well, it's going to be plus 17 meters per second if this is the positive direction. Okay, got to use the same direction as positive. So just because you're looking at it from the perspective of M2, we've already established that this direction is positive, it's going to stay positive. Okay, and this guy is going to see this guy coming at him in the positive direction at 17 meters per second, right? Got to sort that out. Okay, well, anyhow, now if it's an elastic collision, what do we know? It means kinetic energy is conserved. Okay. The final kinetic energy equals the original kinetic energy. Well, right, it's usually written V2 minus V1 which is the relative velocity before I'll use the word initial relative velocity equals might be a little hard to read, but it's final relative velocity but negative, equal and opposite to the final relative velocity. What's the final relative velocity? Well, it's got to be negative U2 minus U1. You've got to remember a formula that applies to elastic collisions. Remember that because if you write out the condition for conservation of momentum and the condition for conservation of kinetic energy, the algebra gets tricky. We can do the algebra and it boils down to this. Now let's just do this, and then we'll look at the equations and the formulas, make sure you see clearly what's going on here. Okay. We know then that after collision, total momentum equals the initial momentum total equals negative 20 kilogram meters per second. And negative of U2 minus U1 equals negative 17 meters per second. I'm going to rewrite that. Take a second. If the total momentum that stands for final total momentum is negative 20 kilogram meters per second. The final total momentum is, I'm debating whether to use symbol or I'm going to just go ahead and use the number, 5 kilograms times U1 plus 7 kilograms times U2 equals negative 20 kilogram meter per second. The kilogram meters per second is unreadable, but it's the same thing I had here, or it might be readable. Okay. And then negative quantity U2 minus U1 equals negative 17 meters per second, and we got a question. Okay, we had a correction. 10 kilograms. I think I mentioned I've been writing sevens where I see other numbers. I don't know. I'm thinking ahead to this. Okay. No excuse. All right. This is a pair of simultaneous equations that you can easily solve for U1 and U2. Now, in general, in the case of an elastic collision, momentum after equals momentum before. That means total momentum, and kinetic energy is conserved, which means that M1 V1 plus M2 V2 equals M1 U1 plus M2 U2. Now that's effectively what I did up here. And I didn't use a formula, I just used what momentum means. But this is M1 V1 and this is M2 V2. I consider that to be obvious. Everybody knows what momentum is. And the one thing everybody got right and wrote down almost immediately, almost everybody, was this. Everybody got this, or almost had it. Okay. Probably had it by the time I picked up the papers. Now, one person got kinetic energies, wrote down kinetic energies. Well, it's relevant, but we're not actually going to write it out. Okay. So there's our momentum conservation. Well, here it is. Momentum is conserved, kinetic energy is conserved. But we're not going to use this. So I'm just going to lightly cross this out, not because it's not relevant, because we're not going to use it. We're going to use V2 minus V2 is a negative of U2 minus U1. And that's what we just did here to get these simultaneous equations. And that's a whole heck of a lot easier than trying to solve when you got U1 squared and U2 squared, V1 squared and V2 squared, okay? Makes sense? That's how you do an elastic collision. Now you can look back at what we did last time also and see that we essentially did the same thing, but I didn't write it out in all its gory detail. So this set of calculations here can be symbolized this way. This ought to be intuitive, at least by the time you get done doing elastic collisions, okay? And it's just, if we're coming together at this speed after the collision, we're going to be moving apart at the same speed. Fortunately, that doesn't happen in football at these speeds. People would get hurt. Both players would probably end up in the hospital if it was elastic. I demonstrated that by walking into the door last time and just splatting against the door, then walking against the door and coming back with the same velocity I started with, right? I hit the door harder the second time, which means the door hit me harder. And I wasn't moving very fast, and that was hard enough. Okay. My shoulders have got a little bonier since last time I did that. Okay, I'm pretty sure this is visible. Got a domino, and I've got a piece of foam, and you see the piece of foam oscillating back and forth. Take this washer and set it down on the end. What's going to happen? Just a small washer. Matter of fact, let's just see what happens if I use a small paper clip. That knocks it down pretty quickly. Okay. Now I could balance the thing. So that the paper clip end is closer to the fulcrum than the other end. Now this isn't perfectly uniform in width. Mass density is uniform. It's kind of uniform. It's pretty close. So this is only going to be approximate, but this thing has a center of mass. And if I was to draw a picture, which I will in a minute, we essentially have two forces acting here. We have the weight of the paper clip at this distance from the end, and we have the weight of the whole piece of foam acting at the center of mass, wherever that happens to be. Okay. Now I can tell where the center of mass is if I just take the foam itself and balance it. Now this isn't perfectly equal to the center of mass. This isn't the perfect position of the center of mass. There's a little bit of uncertainty because this is kind of a wide domino, but that's pretty close to the middle. Okay. So I've marked the center of mass, and we see when this paper clip is balanced, I've got to move the thing over where the center of mass is here. Okay. At that point, I'm supposed to have a meter stick up here. Well, I have the mass of the paper clip at this distance from the fulcrum. And the mass of the foam piece, the foam lever, is about this far. Okay, what's the ratio of those two distances? How many times this distance is this one? Show me with your fingers. That's what I thought. Now you're wrong. Okay, I saw a lot of 7s and 8s. I was thinking about 7. Okay, I could take a meter stick and measure and see who's right, but I don't want anybody to go away feeling bad, especially if it's me. Okay, so the lesson of that is this is exerting a torque, okay? There's a torque. It's tending to rotate it about the fulcrum. And the torque is this distance multiplied by the weight of that paper clip. Okay? And that torque is positive because it tends to go in the counterclockwise direction. Okay? It's going in the same direction that if we went in the positive direction from here using the usual orientation of the XY plane, then the positive X direction would be there, and a positive Y direction would be here. A positive moment arm, that's what we call this moment arm, positive moment arm, and a positive force would rotate it counterclockwise. That makes sense? I'll probably put that in the board eventually, but if I forget, make sure you make sense of it. Okay. This means that the mass of this piece of foam is about 7 times the mass of that paper clip. Because the foam is exerting a torque that's equal to this distance, okay, this small distance here, times its mass. If the same torque is exerted at 1/7 the distance, then the mass has to be 7 times as great, so that the gravitational force, the weight would be 7 times as great. That makes sense? Okay, that's intuitive. That's really kind of obvious. So we'll remember, this is about 4/10 of a gram. If this is 7 times that, we could put it on the balance if I can find it quickly. It's over there. Actually, I'll put it, well, no, I have to get through a couple of things. Okay, I'll put this in the balance eventually, but that would estimate 2.8 grams, which would be maybe 2 or 3 grams when we put it on the scale. If it was a little more than what, it was 1/8, then it would be 3 grams. So in the high twos, we think. Okay. Now let's balance it back in the center so that the beam is exerting 0 torque. Okay. Or very nearly 0 torque. Now, just for the moment, I'm going to put a domino under here. And I'm going to put my small paper clip once more here. Small paper clip is usually about 4/10 of a gram. Big one is usually about a gram. So where should I put the big one to keep this thing balanced? Okay. Let's just say that this distance is 16 centimeters. It's not that far. It's more like 13 or 14, I think. But let's just say it's 16 because that's an easy number to work with. Okay. Then where should I put this one in order to keep it balanced? If I put it on this end, it's going to exert 2.5 times as much torque as this one because it's going to be at pretty much the same distance. from the axis with 2.5 times the gravitational force. So I know if I put it here, it's gonna fall and I'm not gonna wreck my apparatus just to show that. But you can imagine that. So where should I put it? Well, just kind of tell me. Tell me where to stop. Okay, here, that worked. I'm gonna drop it on there. It's gonna stay balanced. Hopefully. I'll gently drop it. Nobody told me to stop. Okay, clap your hands when you think I should stop. And don't clap just because somebody else clapped. And don't only clap once or I'll think that I'm getting thunderous applause here and I don't want to grow a big head or anything. Okay, are we ready? Anybody see where the paper clip is? Okay. Did I just hear a clap? Okay. Did I? Okay, somebody told me to clap. Okay, let's just see what happens. I think it's going to fall. Well, no. It did take the weight off of the. So whoever clapped, you give yourself applause. And if it wasn't a clap, yeah, it was a pretty weak clap, but I'll forgive you for that. Okay. Okay, well, let's see, there's this distance. There's this distance. There it is. It looks like about 2.5 times. If this is 2.5 times the weight of this, then this distance ought to be, well, this distance ought to be 2.5 times that distance. So this distance should be 40% of this distance. All that makes sense? As we're going to go a little ways with it. Okay. That's the end of that demonstration. One of my favorite things is based on this. We can make a very accurate balance with a piece of like the ramp we use, the grooved ramp, and a razor blade. Balance it on. There's a lot to be learned from that about stability of equilibrium and so forth. It's one of my favorite things. I'm not sure we're going to get to it because there are other things that might take precedence. I think we'll at least look at it, assuming I can find all the pieces. Still unpacking. Okay. See what I've got here. When I put the paper clip on this end and the thing rotated like this, what was the direction of rotation? Show me with your fingers. What is the direction of rotation? Okay, well, that's not a vector. That's what everybody's going to say. It's like this, right? That's not a vector. That's a bunch of vectors, and they're all changing through 360 degrees, right? Straight down. Doesn't work because if you had a balanced system with the thing vertical, then you would have to say, you know, with something pulling on it like here. So if we had this thing rotating about some kind of a bearing in an axis and gave it the same force here, it would have the same angular acceleration as it does here with the weight on it. So this direction would be orientation dependent. Okay, if we have it here, you'd have to say, well, it's in this direction. But it's the same torque. Okay, a torque of 0.004 newtons, meter newtons, because that's how you do it. You got point, it isn't 0.04 meter, 0.001 meter newtons, let's say. You just multiply the number of meters by the number of newtons. Okay, and we say meter newtons instead of newton meters, because newton meters is joules, and meter newtons isn't. Call it newton meters. Okay, so we can have the same torque in this position as in this position, but if the torque was down here, it would have to be this way here. But it has the same effect on the rotation of this thing. If I took our rotating system, we could lay it on its side, overlap it over the end of the table, and do everything in that orientation, and it comes out pretty much the same, as long as your system is balanced. So that was a good idea, but no, that's the direction of the force, and that doesn't take account of the direction of the moment arm. Now, I haven't defined moment arm, but it's a vector from the axis of rotation to the point where the force acts, or from whatever point you want to use to the point where the force acts. Okay. This, I know you're in suspense to know what the direction is, so I'm going to have to tell you. You use the right-hand rule. If I've got it, well, it's like this. And I've got to use my right hand, and I can't turn my head far enough to see my right hand. I think it's in the picture. Okay. This is the direction of rotation. This is the direction of the torque. The torque cannot be in the same plane as either the force or the moment arm, because the force and the moment arm can change. Okay. One thing that doesn't change, they can change without changing the torque or the angular acceleration. So this will be our direction. And that makes a lot of sense when you get into the analysis of angular momentum, which we run next week. That's why gyroscopes work. And you can figure out how a gyroscope is going to behave based on this idea. It's a right-hand rule. You know the right-hand rule because you've had, I think, everybody knows how to do cross products, right? You know the direction of the cross product is governed by the right-hand rule. And if you don't know it, go back to chapter 1 so you do. Because I'm not going to explain it. I'm not going to take time to explain it unless you tell me I've read this thing, I still don't understand it. Okay? Then I will take a little time to explain it, but I want you to do the work to understand it. Okay? Right-hand rule. And I'm going to demonstrate, I'm going to use it. So you should pick it up. Also, so if this thing's rotating in this direction, what's the direction of its angular velocity? Its angular velocity is a vector in that direction by the right-hand rule. If it's rotating in this direction, then by the right-hand rule, it's back that way, perpendicular to the plane of motion. So the idea of force, we've got a fulcrum here. And we've got mass here. And a mass here. And we've got a vector R1 here. in a vector R2 here. The net torque is a vector. I'm just, okay, there's M1. And the force exerted on M1 by gravity is F1. And we got M2. There's a force F2. Now we actually know that the force F2 has to be bigger than the force F1, the way I've drawn it, because the R2 vector is shorter than the R1 vector. If I multiply this force by this distance and this force by this distance, got to add up to 0 if it's in equilibrium. Now, we're not necessarily assuming equilibrium right now, but kind of implicitly we're looking at it. Okay, net torque. It's R1 cross F1. Now, how do you get the direction of R1 cross F1? You take your right hand and you put it in the direction of R1, which is this direction, and you turn your fingers toward the direction of F1. Okay, or otherwise use the right hand rule, which you need to be very comfortable with by next time, okay? Well, it's that. Actually, let me write that just in a little more detail. It's tau 1 plus tau 2 equals R1 cross F1 plus R2 cross F2. And of course, R2 cross F2, your fingers go in the direction of R2 and you turn them toward F2, and you see that the torque is into the board. Okay. Equilibrium. If and only if you add those two vectors and you get the zero vector. Now this is pretty simple. You could also have a third torque if this support has significant mass compared to the rest, because you do have a force exerted by gravity at the center of mass. You can consider the support itself to have to be experiencing a torque due to its own mass, and the force being its weight times the distance of its center mass from the fulcrum. There's more about that. I don't want to totally develop that today. I want to really talk about now the beam that we've been studying in lab. Let's say we've got a couple of magnets on the ends. And we've got the axis of rotation. And we've got a pulley. We're looking at it from the top, the pulley's underneath it. There's a big pulley and there's a little pulley. And we got a string extending from this pulley. Now it's over another pulley and then it goes down to, it suspends the weight that accelerates the system. Because of the suspended weight, there's a tension. Now, is everybody with me so far? You understand how that relates to the system? I bring it over here, except that wires are crossed with other things, and I'd probably end up knocking something on the floor. We've demonstrated that a number of times. And now that I think about it, I really ought to demonstrate it. And I think I can move across here and pull this one off. So sure we see it. Conveniently, this thing actually has a suspended weight, so I can demonstrate it, maybe, and get it unraveled. And every time I try to unravel it, it gets messed up. Okay, you see, I've got these paper clips suspended here, okay? Now the string ideally goes around the pulley, okay? So we can see the pulley underneath here with the string on it. There's a bigger pulley right here, and you can see the roundness of that. Then there's a smaller pulley here, and you can kind of see the string, white string outline around that smaller pulley. Okay? If this thing wasn't wrapped around the axle, then there would be a tension in the string. If the string was over here, suspended from the edge, and I'm probably blocking everything, it would be exerting a force at the rim of the pulley that's equal. I'm going to get this thing to work for, well, don't want it to kill me, so I don't know what to say, but it might be worth it. Okay, there we go. Okay, there it is. Now, can you see that the string is suspended from this inner pulley? So that if I release the system, there's a tension in this string. Now, when I release the system, the mass at the end of the string is going to accelerate downward, meaning the tension is going to decrease a little bit, but it's not going to accelerate very much. So if I can get out of the way, we can see what happens. What happens is what we expect. We get a rotation and the pulley got caught. Let's try again. See if I can keep the thing from following itself. Okay, here we go. Okay. Now I'm not really in any great fear here, but eventually this thing's going to go fast enough, take the tip of my nose off, and we'll just let it stop there. Now that's familiar because you've studied that thing and analyzed it, not necessarily a vertical position. But I want you to carry that image into what I'm saying. Now, when I had it, the tension, the other thing was on its side, the tension's, maybe the thing is up, maybe the string is hanging from this end, so the tension is down this way, okay? Doesn't matter. Or think of looking at the system that we're used to from above. Here's the edge of the table. There's a pulley out about here, and the mass is suspended over that pulley. It's going to give this thing an acceleration. The tension is exerting the torque. The point at which the tension is applied to the system is here. And you have an R vector here. Okay. Now what we have there is maybe 6 grams of mass at the end of the thing. So my example the tension would be approximately 0.06 newtons. I do want to do the vectors. I want to write the tension. Okay, we'll put that in the I direction because that's where the standard I vector would go with a coordinate system with the x-axis horizontal. Okay, suppose the tension is 0.06 newtons times I, and R equals 2.5 centimeters times the J vector. Because R is in the direction of the J vector, right? I drew it. Then the torque equals R times T. R times T, the cross product of the R vector with the tension vector. What's that cross product? Give you about 30 seconds to write down what the cross product would be, maybe a minute, give you a little time to think. Okay, so this equals, I'd write it lower, but what I see on the screen doesn't ensure that it's going to be visible. I'm pretty sure it is, but okay, we multiply 0.06 newtons times 2.5 centimeters, which gives us 0.15 Newton centimeters times the I vector crossed with the J vector. Now, if the x-axis is here, so the I vector is in this direction, the J vector is in this direction. If we do the cross product, I cross J comes out this way, right? And that corresponds to a vector in the positive x direction, a vector in the positive y direction gives you a vector in the positive z direction. And that is what will result in a counterclockwise torque. So this equals 0.15 Newton centimeters times K vector, which is and I'm usually going to write meters times newtons, so we don't. I recommend you do that so you don't start confusing that with joules, because we're going to have joules in this thing too, okay? I mean, we get joules of energy when we do this thing with the beam. Does that make sense? And you should understand that a centimeter is 0.01 meter. If you multiply 0.01 by 0.15, you get 0.0015 meter newtons times your K vector. And that's going to be constant on this system, because as this string unravels, you're always going to have tension force applied to the system at the same point. Now, if I had the beam with a little fan on it, and that fan was blowing air this way, it would accelerate the beam around like so, right? So the direction of the force from the fan would always be changing. But still, your R vector for the fan force, if the fan force is like this, your R vector would be down here and the fan force would be here. You would do R cross F, and it would still tend to accelerate the system, but that can't be right. If the fan is blowing that way, that would accelerate. Something's wrong here. Okay, my right-hand rule is wrong. I'm sure Trey picked it up, but if I do R cross T, and I said this is a positive Y direction and a positive X direction, well, it is positive. But that torque there would tend to rotate the thing in the negative direction. So what's wrong with my thinking? Well, I told you the right-hand rule is pretty simple. It's simply that R is in this direction, T is in this direction. The force is into the board. And that seems to contradict something I said earlier, but I don't think it's going to trouble you. Okay, so R cross T is this, and this is times I cross J. And it isn't I cross J because the R vector is in the J direction, and I wrote it down incorrectly. My I's should be J's and my J's should be I's. 0.06 newtons. Don't do like I do, write this down carefully. R is 2.5 centimeters times J cross 0.06 newtons times I. Now that was a bonehead mistake on my part, but it's J cross I. And J cross I is negative K. Put the negative sign out in front in the final result. clearly, I'm doing R cross T, R has to be written first. And the order of the cross product makes a big difference. If you're crossing this into this, you get a force in this direction. If you're crossing this into this, you would get a force back in this direction. This will tend to rotate the system counterclockwise, which agrees with the fact that we have a negative multiple of the K vector. We have a negative net torque, giving us an acceleration in the negative direction. Now, one other thing that's a little bit weird. Hey, let's say we've got the same system. Pulleys there, but we don't have the string with the suspended mass. Instead, we attach a string here. Let me give the string some color. Attach the string here. And give it a tension. Our R vector goes from here to here. R cross T has a magnitude that's equal to the magnitude of R times the magnitude of T times the sine of theta. Where theta is the angle between R and T. We could extend R out here and theta would be this angle. Or if you like, theta is this angle. It doesn't matter whether theta is this obtuse angle or this acute angle. They both have the same sign. They're supplementary angles. They have the same sign, and you can work out why that's so. Okay. Now, what's the direction of the cross product? Because so far we just have a magnitude. What's the direction of R cross T? Well, you can see that if I pull on a string in this direction, it's going to tend to rotate it this way, right? So it's got to be negative. But you can also know that R is now in this direction, and you cross toward T, it's still going to point into the port. But R doesn't make a 90-degree angle with T the way it did here. So you don't just get to multiply these numbers. Okay. Well, it'll be times negative K. If I gave you this vector and this vector in components, you'd be able to do the cross product. Okay. And you need to be able to do that. Quickly, there's one more way to do this. I know we're out of time. If you got to go, just walk out. But the extension is here. Here's your line of force. If you go from here straight over to the line of force, you've got this vector. With the notation I've got here, the length of this vector is very clearly R sine theta times the I vector, where R is the length of this vector. You just got a right triangle here. Right there's your opposite side from the angle theta. Okay? So this vector down here is R theta times I. And if you do this crossed with this, you just got I cross J, which gives you negative K. And your magnitude of R, magnitude of T sine theta is already taken care of because of the R sine theta. So that you can use the vector from your axis of rotation to the line of force perpendicular instead of using this vector.
Hey, Jason.
You're going to see that if you read your text. Okay, sorry for keeping you 2 minutes late. A little bit careless at the end. The R cross T was kind of cut off. But the camera